In this video, we're going to see how we can start off from a Poisson process and arrive at a gamma distribution. You'll see that this is actually very similar to a video I did before on the exponential distribution, where in that case, essentially, we're just dealing with the case where n is equal to 1. And in this case, we're just going to generalize into all other possible values where n is a natural number. And what we get in the end is the gamma distribution. So of course, the gamma distribution can also be generalized into cases where n is not a whole number, can be any other number. But in our case, since we're starting off with the Poisson distribution, we'll arrive at a case where n is a natural number, and this will show you essentially how we can arrive at the gamma distribution from a Poisson distribution and give you a concrete example of how we can interpret the gamma distribution. So what exactly is a Poisson process? You can think of this as a random variable xt that models the number of random occurrences that happen within time t. So you can think of x as kind of like modeling the number of phone calls we receive, and in our case, let's say t is equal to 2, so that will model within this period the number of phone calls that we receive, and which is of course a random number, and that random number will follow a Poisson distribution with parameter 2 lambda. So that's what a Poisson process is. So let's say given this Poisson process, we want to investigate the amount of time we need to wait before we receive n phone calls. So what will the amount of time be? So since the amount of phone calls that we receive is random, the amount of time we need to wait before we receive n phone calls is also random. So let's say this amount of time we need to wait is a random variable t. And so it turns out this t is actually the gamma distribution, and that's what we're going to show in this video. So to find the distribution of our random variable t, let's consider the probability that t is smaller than or equal to some constant t. Now what this means is that within our timeline from 0 to t, we know that our random variable is smaller than our t. That means at some point within this time period, our nth phone call was received, because when we receive our nth phone call, that's the amount of time we need to wait before we receive n phone calls. So that means if our random variable t is smaller than t, that means within this period, we must definitely have n or more phone calls. So an equivalent way to express this expression, our random variable being smaller than or equal to small t, is to express this using our Poisson process. Another way to write this is to express this as xt is larger than or equal to n. So these two conditions are completely equivalent. So now we've jumped from this expression to this expression, and since we know the distribution of our Poisson process, we can now rewrite this in some more concrete terms. So let's rewrite this as 1 minus xt is smaller than n. So that's just the complement of this above condition. And now we can use the definition of the Poisson process to rewrite this expression. So we can rewrite this as 1 minus, starting from k equal to 0 to n minus 1, because we're considering the number of occurrences that is smaller than n, and a Poisson distribution can take on integer values from 0 all the way to infinity. So this would essentially mean we're considering cases where we get 0 to n minus 1 occurrences for xt. And for xt, this random variable follows the Poisson distribution lambda t, and so that's why in this summation term we get e to the power of negative lambda t to the power of k divided by k factorial. This is just the Poisson distribution. And now we can try to rearrange this term a bit in order to get back the distribution of this random variable t. And now in order to do that, since this is what we call a cumulative distribution, we can actually differentiate this expression to get the probability density function. So the probability density function is just the derivative of this expression, the cumulative distribution function. And so essentially what we have to do is to differentiate this summation term that we have. So obviously you can see that the 1 will disappear after the derivative. So all we have to do for the rest of this video is to find this derivative. So continuing on with our derivation, so this term turns into 0, and then in the summation term, we will have this expression. So we will have to use the product rule, so we will differentiate this term first. So we have negative lambda e to the power of negative lambda t, and then multiplied by this original expression, so we get lambda t to the power of k divided by k factorial, and then we will also get this term, e to the power of negative lambda t, and then we will differentiate this term. So we get t to the power of k, so that just becomes kt to the power of k minus 1. And then we still have this k factorial down in the denominator. So let's try to rearrange this a bit to see if we can simplify this expression. So the first thing we can do is to pull this e term out because it just gets in the way. So let's just pull this out. And then I'm going to separate these two expressions into two summation terms, and you'll see why in a sec. So we've pulled this out, and let's just put this negative sign back in to keep things simple. So we have this lambda to the power of k already, and we have another lambda here, so we get lambda to the power of k plus 1, and then we also have t to the power of k, and then we have k factorial. And then this plus sign becomes a negative, and then we have negative, and then we're going to start with k equal to 1. And the reason is because we have this k term over here, so when k is equal to 0, this entire term is just going to be 0. So it's a bit redundant to write that out. So let's just put k equal to 1. And then the remaining terms inside this summation term will be lambda to the power of k. And then we also have t to the power of k minus 1. And then we have this k factorial in the denominator and this k in the numerator. So that just becomes k minus 1 factorial. And so this is what we have. And you can see that these two terms look suspiciously similar, so we can actually cancel some of these terms. And in order to see that more clearly, we can define L to be equal to k minus 1. I'm just going to change the indexing term over here. So let's just rewrite this as so. So this is we'll just retain this term over here. And then for this summation term, so when k is equal to 1, that means L is equal to 0. And k goes all the way to n minus 1, so in that case L will be n minus 2. And then lambda to the power of k will just become lambda to the power of L plus 1. T to the power of k minus 1 will just become t to the power of L. And then the k minus 1 factorial in the denominator will just become L factorial. And then now you can see that these two terms are essentially identical. So the only thing that's different between these two terms is the indexing in the summation term. So you see that all these terms, they actually all match and will cancel each other out, except for the n minus 1th term in this expression, because this only extends to n minus 2. So in the end, the only surviving term will be the n minus 1th term within this expression, as everything else cancels out. So in the end, we have lambda to the power of n, because we have n minus 1 plus 1, and then t to the power of n minus 1 divided by n minus 1 factorial. And then, of course, don't forget the e term that has been sitting outside the bracket this whole time. And so there we have it. This is the probability density function of the gamma distribution. So what we've shown in this video is that starting from a Poisson process, we can actually derive the gamma distribution. So what this means is that we can interpret the gamma distribution as essentially the amount of time we need to wait before receiving n phone calls. And so this gives you a concrete way to understand how we can interpret the gamma distribution.